Hello all, this is Chandrakant from Mayachitra. In this talk, I will be presenting our ICIP 2025 paper called MetaReg. And in this paper, we propose a method that can do robust camera parameter estimation by leveraging noisy camera extrinsics. This work has been carried out as part of a collaborative project between Mayachitra and Johns Hopkins University. Here is the outline of the talk. As part of introduction, I will be discussing the problem statement that we are trying to solve in this paper, and I will be presenting several challenges that traditional SFM solvers face. And then I will be presenting our proposed solution, MetaReg, where I will go through how we leverage noisy extrinsics to boost structure from motion or 3D reconstruction. And then I'll be presenting qualitative and quantitative results of the proposed solution. And at the end, I will conclude this talk by discussing potential future research directions in which MetaReg can evolve into. So let's get into the talk. When it comes to reconstructing large-scale scenes from unordered collection of images, existing out-of-the-box SFM solvers like CoalMap or GlowMap, they really struggle to come up with point clouds and camera parameter estimates that look something like what we show here in this slide. And the main reason for which these SFM solvers struggle a lot is due to the fact that there could be a lot of doppelganger structures in the scene, and at the same time, there is a possibility to end up having fragile scene graphs due to really sparse overlap in the field of view across images, or due to heavy perspective distortions between some of the image pairs, or it could also be even due to a feature matcher that is designed to be precise enough for dropping doppelganger pairs. When I say doppelgangers, or when I say the presence of doppelganger structures might hinder the performance of SFM solvers, what I mean by that is any real life scenarios, uh, there will be many structures which are engineered to look exactly the same. Like, for example, right, like if you look at this particular JHU campus, all the windows might look exactly the same, or left side of the building might look exactly the same with respect to some portions of the right side of the building. Or, for example, here in this particular example, the front door and the back door look exactly the same. Like the windows look almost the same, and the text that says Johns Hopkins University Applied Physics Laboratory, the text look exactly the same. And what happens is, in the presence of doppelgangers, when we do pairwise feature matching using methods like superpoint superglue or Roma or master, they propose lots of confident point matches between these doppelganger structures, and this leads to a lot of false positive edges in the scene graph. When I say scene graph, what I mean by that is it is something that I'm showing here in this screen. If we consider all images, or basically all cameras in the input folder as nodes in the graph, and if we add edge between each pair of the nodes whenever a feature matcher proposes geometrically verified point matches between that pair of images, it leads to a graph-like structure, right? And this is what we refer to as scene graph in this context. So one of the challenges that SFM solvers face here is that these scene graphs tend to get fragile, especially when we try to be more precise and remove all doppelganger pairs from the scene graphs. And this fragile scene graph can force SFM solvers to generate disconnected point clouds, which is not good for underlying tasks like novel view synthesis. So just removing doppelganger pairs and making the scene graph more precise would not solve our problem. So in this paper, what we try to explore is basically many of the cameras nowadays are being attached with GPS devices, be it our iPhones or be it our drones or be it some GoPro cameras. All these devices are coming with default GPS enabled devices. And we have basically tried to leverage this fact and see if we can somehow use this noisy GPS metadata that is being associated with these cameras and boost the performance of any of the existing SFM pipelines. And at the same time, we try to ensure that the proposed method is not just compatible to one particular SFM solver, but instead we explicitly try to make sure that the proposed method is kind of compatible with any of the SFM solvers out there, like GlowMap or be it GlowMap or some other methods like OpenMVG. So let's look into our proposed solution. In this paper, we propose MetaReg, where we try to leverage noisy GPS metadata associated with the cameras to boost the performance of SFM solvers, both with respect to runtime and also with respect to geolocation RMSE of camera poses. We achieve this by introducing two modules into the existing SFM pipeline. First module gets invoked before running SFM pipeline, where we basically look at camera GPS metadata and predict if a given image pair has an overlapping field of view or not, based upon the distance between both the camera's noisy GPS coordinates. And this will basically generate a scene graph which can be used to run the SFM pipeline. And once the SFM solver has finished running, we invoke our second module called modal merger. And if the SFM pipeline generates more than one cluster, this module will basically merge these disconnected point clouds into one final cohesive point cloud using GPS aided procrustes aligner. So let's do a deep dive into our pre-SFM module, which we call it as overlap estimator. And what we did here is, once we have the unordered collection of images, instead of preparing the scene graph by just matching each image with every other image in an exhaustive manner, what we did is we first pruned the scene graph. We first prune the exhaustive scene graph using some existing overlapping image pair estimation methods like netville or eigenplaces, and we take the union of the pairs proposed by these two methods, and we treat them as the filtered image pairs, or basically the filtered edges in the scene graph. And on this filtered scene graph, what we do is we take the camera GPS coordinates of image pair that corresponds to each edge, and if the GPS coordinates indicate that the cameras are separated by a large distance, like let's say more than 50 meters, we consider that image pair as the invalid edge in the scene graph. and and yeah, one could argue that this might lead to loss of many true positive edges in the scene graph, but what we do is we invoke SFM solvers using this sparsified or pruned GPS based scene graph. And then at the end, once we finish running the SFM solver, and if this sparsification actually lead to disconnected point clouds or fragmented point clouds, we have our post SFM module to merge them back, which I will be discussing in this slide. So basically, we do the merging of these point clouds post SFM using our modal merger module. And what we do here is we start with the fact that SFM solvers might end up having more than one disconnected cluster, as we have sparsified the scene graph as I explained in the previous slide. So we take each one of the disconnected cluster and extract the camera coordinates with respect to the cluster's relative coordinate system. Just because these SFM solvers do not produce point clouds in the metric scale, they have their own relative coordinate system. And then what we do is we use procrustes aligner to align the cameras in relative coordinate system to world coordinate system, by assuming the fact that each camera is associated with a noisy GPS metadata. And we do it for all the disconnected clusters and bring all the clusters into one coordinate system, where here it's the world coordinate system, and merge all of those point cloud slash clusters into one cohesive final point cloud. And this pipeline has enabled us to come up with really good quality, camera parameter estimates, and cohesive point clouds, which helped us reconstruct several large scale scenes. So let's look at some qualitative and quantitative results that we got from this method. So here is one such example from Ultra dataset where there are around like 500 images coming from the JHU APL building, and these 500 images are kind of spread across the building, and all the images are ground. There are no drone images, and if you look at it like uh, of since we run the SFM solver with our sparsified distance based scene graph, what we got is like we ended up having like four disconnected clusters as the output of Colmap. Here we used Colmap as the SFM solver, and all these four clusters, if you look at it, what we did is like even though they do not have any overlapping cameras, what we did is like we basically aligned all of them into one coordinate system using the associated camera noisy GPS metadata, which we have shown in the uh, top row of the figure. And we basically aligned this Colmap clusters which are in the relative coordinate system into a coordinate system so that they are kind of in accordance with the noisy GPS. And then what we do is once we have this aligned point clouds or camera poses plus point cloud, we kind of merged all these four clusters into one final cohesive cluster, and this cluster has both camera poses and also the merged 3D points, and this cohesive cluster can be used for downstream tasks like novel view synthesis using nerves or Gaussian splatting. And here are some quantitative results where we show that with noisy GPS, there is definitely significant improvement in the geolocation RMSE. And we evaluated this on 4 scenes from Ultra datasets, which are publicly available. So when it comes to future work and the summary of the talk, so we develop MetaReg, and one could potentially enhance the MetaReg to many outdoor and indoor scenarios, and one could actually come up with better overlap estimation module based upon, let's say if it is outdoor scenario, one could potentially use the OSM street maps to understand if the cameras are coming from the opposite sides of the building or cameras are coming from the same side of the building, and that can help us prune the scene graph in a much more precise way. And when it comes to indoor scenarios, of course we cannot use OSM footprints, but if there are any available building footprints, then that would help us understand if the camera is coming from a given floor or from the different floors or from the opposite corners or from different rooms altogether, and that can be used to prepare precise scene graph. And then later we have our robust model merging algorithm which is based upon Procrustes aligner, and that can be used to merge all the point clouds into one final cohesive point cloud. So this is something one could explore, and we are actually looking into it. And to summarize my presentation, we basically wanted to say that by addressing key SFM challenges like doppelgangers and fragmented reconstructions, MetaReg basically made the large scale 3D reconstruction more accurate, scalable, and basically it made it easy to generate 3D scenes at scale. Thank you very much for listening to my talk. Hope we all can meet at ISIP.